discuss some of the benefits of using phased array in Luer radiography, and with that goes distinctive advantages as well as disadvantages. So we'll talk about that. As it pointed out in the program, I'll actually go over some data as well, show you what the technicians in the field and ultimately people are faced with analyzing data. And also touch on some high temperature, the ability to do phased array during the welding process, possibly, but certainly between stages of welding. So why use phased array? You know, you got film, you got phased array. You know, what decision process do you go through? At the end of the day, in my opinion, it comes down to what? Cost, mostly cost. There are some other advantages. Some progressive owner users and clients are going green, no chemicals, no film, less radiation, and there is that. And many times we're finding that cost isn't a big issue with the certainly the owner user. Still is with the fabricator. The fabricator, at the end of the day, he's going to have a budget for inspection costs, and if the higher cost is imposed upon him after he's actually budgeted the job, then at the end of the day, cost does become an issue. Also, in-service inspection, complex geometries, at the end, really phased array is about the imaging. We're going to focus on in lieu of radiography. I'm sure Dr. Moles talked about the code, the latest in code. I really wanted to be here for that to make sure there was no conflict in my presentation, but I missed that, I apologize. And then again, like I said, the cost savings. So everyone's aware what phased array is, so I'm not going to dwell on that. I will just say that the difference is having a single line, conventional ultrasonics with basically a single A scan, whereas with phased array you have multiple A scans all harmonized together to produce some sort of image. And again, it's all about the image. This is one of the Olympus slides, if you will, here, just showing the advantage of rather than looking at an A scan and trying to picture in your mind what you're seeing graphically, you're able to see an image and see it real time and see what it looks like. So that comes about, just here's an example of such. In this case, a delayed crack on a nozzle, being able to see a crack, technician now having an A scan, being able to visualize what that crack is, move his probe back and forth, determine what the profile of that crack is, where it's at, et cetera and so forth. Whereas with phased array, you're able to actually see that crack in its entirety from one probe position in this case, because the crack is within the beam area. So you can actually see the shape of the crack, location of the crack. You can actually size the crack. Ultrasonically with pulse echo, you're moving the probe. You're going to be able to see the tip at a certain time, maybe able to size it, and then come back and see the crack at the base where it starts. Maybe not necessarily along the face, but here you can clearly see and connect the dots. You have one continuous crack propagating straight perpendicular up the nozzle well. And again, being able to put that image into a graphical representation like this, rather than turn in a report that says manual shear wave was performed, a crack was found, given this depth, this location, which is fine, all the results are there. At the end, you get the information, but actually having the ability to see the crack for yourself, the owner user, the fabricator, whoever, being able to actually validate the findings much more clearly than they would from a simple handwritten report. There's essentially 5 categories as I see it in phased array. The manual phased array, non-encoded, and there's the encoded. There's the semi-auto, using single axis encoding, and then fully auto, using single or multi-axis encoding, and then fully auto high temp, which is multi-axis encoding. The 5th one's kind of a new one. And details on each. Here doing manual UT. Basically, the guy's reading live images on the screen. ASME, ANSI B31.3 piping, process piping, they're still allowed to do manual shear wave. So now stepping it up a bit, using phased array in the manual shear wave mode, you're able to get a higher confidence, possibly get a productivity enhancement, but hopefully at the end get better quality results. Still, just a simple image looking at a screen, almost like shear wave on steroids, as I put it sometimes. And then manual phased array encoded. Here, stepping it up a bit with a simple encoder, so storing the data, not that you couldn't store before, maybe in time-based, but here storing the data in encoded position. Either a series of scans at fixed access points from the weld, or simply just storing the data so that you can recall it and then take defined length measurements. In the manual mode, without an encoder, you're relying on the technician to start and stop and mark the weld and take those measurements. Here you're relying more on the data and the accuracy of the encoder to do that for you. And then semi-automated. Basically, it's more of a rigid type scanner, a chain scanner, or at least a scanner of sort, but without power. It's moved by hand. Here using multi-probe assembly on each side of the weld. Again, same scenario, storing data, ability to pull it up, recall it, get defined measurements, etc., and so forth. And then fully automated. Fully automated makes use of robotic scanners. Some say it's higher accuracy. Depends on the technician. On manual semi-automated mode, when you got a manual scanner, the technician may not be able to keep that position concentric to the weld. He may drift one way or the other. It is in hopes that with an automated system, if not on a track or a scanner or a chain type setup, that you have a laser guiding it, and you're able to control the accuracy much more, keep that scanner on track, and hence have higher reliability of your data. And then the last is using high temperature scanners, basically scanners, in this case, capable of doing scans up to 600 and 700 degree F in temperature. Again, same scenario, multi-probes. So phased array equipment. There's all sorts of equipment out there. Some doing manual scanning. The Olympus equipment here that handles certainly automated, semi-automated, as is some instrumentation here as well, not to mention the probes. Out in the shop. So we've got the advantage of doing equipment or inspections out in the shop in lieu radiography, or possibly in the field. In the field, the impact is much greater because there's a lot more activity in the field, in the pipe racks, or out in the units, wherever it happens to be. But even in the shop, in this case, this is a rather large shop, and it's got no less than 150, 200 people in there welding on these sections at the same time. And while that inspection's going on, or while all the activities are going on, the inspection's simultaneous. They don't have to wait for night shift to do radiography. In this particular case, we're talking about heavy wall vessels, heavy wall components, bringing cobalt in, stuff like that. It definitely shuts down the operations. Offline analysis. So, with the film, you get basically more 2D representation, or one plane, if you will. With phased array and TOFT and all the ultrasonics, you have the capability of also getting depth placement, height placement, be able to accurately size and get the information you need. Whereas with an X-ray, it all comes down to the classification of the flaw, what type it is, and then how long it is, or how much that particular anomaly is in the weld. So why phased array at all? Why even ultrasonics and low radiography? Well, there's some distinctive benefits. Typically, you don't have to shut down, like I said, other work activities, no radiation sources, also a safety benefit. It's getting increasingly harder to use radiation, and certainly ionizing sources. And who knows with the safety protocols in place, I'll be honest, it's public record. We had a source stolen about 8 months ago. It was never recovered. To this date, it hadn't been recovered. If that goes on with other companies and happens more and more, you may find regulation a lot tighter on sources and the use of those kind of sources. Increased productivity, absolutely. Especially the thicker the component, obviously the larger the benefit. Most of the X-ray we're doing now out in the field is on the smaller components, small diameter piping, thinner materials. Reactors and vessels almost always are getting UT low radiography now. Permanent records, of course. I think the tendency before, certainly ASME did allow manual shear wave, and they still do on nozzles for that matter. Hydro being the prevailing end result or end exam on a vessel. But now the ability to actually have the images makes it a viable option for quality, both quality and the ability to to sign off on that particular vessel or component. Not to mention the quality value, better differentiation of critical flaws. X-ray's always been a little bit limited, certainly in depending on some weld joint designs, and on non-fusion, planar flaws, transverse or delayed type cracking. Radiography doesn't see it very well. So if you got embedded cracks, it gets increasingly difficult. Obviously, safety factors were designed into the process so that those kind of flaws, everyone knowing they'd be missed would be acceptable. But now you have the ability to see basically anything and everything. That's both an advantage and disadvantage. Now you can actually see everything. So the welders have to tighten up as well. Could result in overall cost reduction. Notice I said it could result. It doesn't always result in cost reduction. Sometimes it's more expensive to do this level of ultrasonics than it is radiography. The disadvantages. Typically additional upfront time or cost is required. Unfortunately, still to date, you got to qualify on mock-ups and calibration blocks. It's almost like a welding procedure where every single job and every design you got to requalify, even though it might have been done 100 times before. So those costs add up, so that is a disadvantage. Piping calibration blocks. It's gotten a little bit nicer now in 2010, but before you had to have a pipe block for every diameter and thickness, which means you could have hundreds of calibration blocks. Now the diameter and thickness tolerance have been put back in, so it makes it a little bit easier. Code case, in my opinion, is way too complicated. Of course, I missed Dr. Mull's presentation. I might have had a little revelation there, but I still think it's very complicated code case to work with. And it certainly requires education of not only the fabricators and owner users, but even the people that are executing the inspections, service companies or the NDT providers. May be considered too sensitive. Like I said, in general, when the techniques are applied correctly, it's highly unlikely that you will miss anything. From micro non-fusion to small porosity, I mean, you literally see almost every flaw. In many cases, welders aren't used to welding at that quality level. The very first exam you start and you see all these flaws and they just, they don't like it one bit. They go in there with arc gouger and they don't find the flaw. But when they go in there and start grinding, then they can see the flaw develop as they get to it. But yet it's still very small flaws. So again, many times it can be too sensitive and the fabricators aren't used to doing that level of welding. Unlike RT, the comprehensive images may not be readily reviewed by third parties or clients. I think there's not an AI out there in the country that can't look at a film and at least have an interpretation on it. Everyone's used to looking at film, but not these images. So it's very limited, the people that can interpret these images. So then it falls back on the inspection company. So the owner, user, or fabricator is relying on confidence that that person interprets that data correctly and produces a report. So, however, with minimal training, we've shown that training the AIs, training the owner user, that anywhere from 4 hours to 8 hours, sometimes a 2-day course, you can get a pretty good understanding of these images and how to interpret them. At least, many times you don't have the benefit of the raw data. The end product might be in the form of a printout or a file that shows you just a snapshot. But the ability to actually interpret those snapshots is still important. Initial direct cost comparisons may seem high. However, with no work stoppages performed, inspection and actual cost savings can be achieved. I think that's true. But like I said, buying mock-ups, buying probes, developing a procedure, getting it qualified, there's a pretty good initial upfront cost. With radiography, what do you got to do? You don't shoot a test block to make sure you saw the non-fusion that's in it. I mean, you don't even have to qualify radiography, you just have to shoot. So there's not really a whole lot of upfront cost in radiography. Potential time savings. So let's first look at time savings versus cost savings. So a typical inspection activity, and I picked a 12-inch Schedule 80 pipe weld. To prepare it, which is basically just load your film, pick your film, design your technique, calculate your shot times, get a JSA, possibly a permit. Versus ultrasonics takes a little bit longer. It certainly takes longer to calibrate an instrument versus just slamming some film into a cassette. So it takes a little bit longer to prepare. The exams itself, however, in this case a 12-inch exam, the guy's set up ready to go. It takes less than, I put actually down 6 minutes there, but depending on if you're in a shop or out in the field, but in the shop, I mean, literally it takes 45 seconds to a minute to do the inspection on the weld. To do it with radiography, you got to take a minimum of 3 shots if you're not doing a panoramic. That's in this case, I just figured on 3 shots. And then to develop the film, at the end of the day, you ended up with about 30% time savings in this particular application of a 12-inch schedulated pipe. So comparison, we'll do a little cost comparison here too, as well as time. So I pick either one, and basically a 1 shift period, assuming you're shooting at windows, lunch, shift change. And you could probably knock out 12 8-inch pipe with 1 crew, or maybe 4 24-inch pipe. At the end of the day, I just picked basically 27 linear feet you can expect from 1 radiography crew, probably, versus 95 linear feet with a phased array crew, linear feet. In this case, I picked this particular one, I believe, yeah? 4, yeah. But at the end of the day, we're looking at about a 58% savings in cost or time, depending on how you want to factor it in here. Time is cost, and cost results in time savings as well. So overall, for that kind of productivity and volume, you could expect a pretty good cost savings in using certainly UT and other radiography. Now, if you're just interested in one particular weld, one weld only, most likely it's going to be much more expensive to do phased array than it would radiography. So a little bit on high temperature exams. Let's talk about basically a heavy wall reactor in this case. Now, most of this has come about as a result of doing on-stream inspection. But lately we've been getting more and more inquiries on doing some fabricating inspections. 2 1/4 chrome materials, heavy wall materials that you got to maintain a 400-degree preheat throughout the entire welding process. Now the ability to actually inspect that maybe after the 3rd pass or 4th pass or even midway through, and being able to find a serious flaw before you weld it completely out is a big benefit. So in this case, I'm just showing the sensitivity, basically looking at an ID notch, typical for an in-service inspection, but I'll show you another example in a second. We had basically a TC down here monitoring the temperature, but being able to see this at 600 degrees F is pretty powerful. So here's an example of an ambient response on a cow block. On the left, you're seeing the response from a notch. On the right, you're seeing the response from a side drilled hole. That's at ambient, and this is at 600 F. So there's not a whole lot of difference between these two. So the ability to do this kind of inspection at temperature certainly is viable in this case. Here's an example of a fully automated reactor inspection, if you will. And what we'll do is we'll launch into trusty beam tool here, assuming it works. There we go. So it's tools like these that make it easy for technicians, or certainly the level 3s, to design probes that you need to use, the coverage that you expect to get on a weld. And it's almost very difficult to do something like this without these kind of tools. I just wanted to show an example of how a person sets this up with multiple probes. We've got a set of TOF probes here. We can turn off the beams just to see the TOF if we want. Actually, it's a little hard to see the TOF, so let's go in and configure that. Let's make it a little easier. Let's go with that. There we go. It's a little easier to see the TOF. So the technician can calculate where he needs to put his probes to get the coverage he needs. He needs to cover the bottom third of the weld, the bottom half. He needs to cover the upper part of the weld. If you don't know it, I believe there was a TOF presentation earlier, but although in my opinion TOF cannot stand alone, you typically have to supplement with shear wave with some other technique. Phased array has its ability to actually stand alone. You can get the coverage. It's hard to get away from TOF though. Its ability to actually see flaws with ease, and it's a good technique to really complement the phased array with. Before we were complementing TOF with something, now we're complementing phased array with the TOF. It works out both ways actually. But here you can see how a technician can set up his coverage. He can actually go in control how he wants to, what angles are required, simple key of a button. Owner users and fabricators could have these programs and could actually do these kind of calculations up front, much like doing a WPS or working on a welding procedure. You guys could actually dictate to the inspection service provider, I expect you to get this kind of coverage, here's the beams I expect you to use. I mean, there's no really limit to what you can do with this kind of tool, either on the front end or the back end. Everybody see how easy that works? Good. Don't save. All right, now we're looking at some data here. This happens to be some high temperature data, but again, the ability to actually see graphically what we're looking at, superimpose welds into the data, being able to see both sides of probes, one side of the weld versus the other, merge the data together, see it in C-scan, top view, see it in a projected view. You know, these views just get endless. Let's launch into TomoView here real quick. Unfortunately, TomoView expects you to go find it. There we go. So I pulled up a set of data. First thing I gotta do is go find my well. All right. So a technician, it's one thing to collect the data. It's another thing to actually go through all the data. So the technician is forced with going through all this data. I've got it set up so I've got one cursor on one side of the weld. I can't find my red cursor now, but there they are, I believe. Oops, let's push the mouse right here. So in this case, scrolling through the data, I can see I've got some pretty good ID weld geometry up here. And as I come through and move and scroll through the data, I can quickly see that a crack has developed. Certainly you can see it in the merge. Let's see if I can zoom this up a little bit more for you. Let's go back through here. So the technician has the capability of not only defining the length, start points. At the end of the day, we don't care what the maximum amplitude is here. We're dealing with a crack or we're dealing with a flaw. Really what we care about is the endpoints and the depth through all location. All that's available in these kind of tools. They do have a reader version or basically I call it TomoView Lite, if you will, that does give owner users and fabricators ability to actually do some limited manipulation or view of data. But at the end of the day, what you get is you get a presentation and a report that probably has cursors positioned over the most favorable, what I mean by favorable, the most detrimental portion of the flaw, one would hope. Or it could be positioned, you might see it positioned here with a definition of flaw length from here to here. You may pose back a question, well, what about this over here? You chose not to call that a crack. Know a little bit more about the images, you could say, hey, go by and show me this other section as well. The bottom line is you've got all these analytical tools at your fingertips capable of actually analyzing the data, both in what it is, where it is, how high it is, how long it is. Very powerful tools. All right, let's get out of here. Continuing on, same thing, in this case a nozzle, and we don't need to launch into this one, but basically at 600 degrees being able to see a crack in a nozzle, much like at 400 degrees being able to see any flaws developing in a weld. Code compliance. I'm not going to talk about this too much other than the complicated nature of it. ASME, of course, Section 1 and Section 8. Been real avid users of UT and radiography. B31.1 power piping as well, B31.3. Section's pretty much covered in the ASME code now. You'll see some minimization of some of the code cases, which is nice. But notice that the piping code, specifically B31.3, still allows manual shear wave, even class 1 piping. Now what you find is most people are either not doing shear wave and mandating radiography because it's critical welds, class 1, it might be 3,000 PSI, hydrocarbon of some sort. You still struggle with people accepting a manual shear wave exam, even though the code will let you do it. But with phased array, you're able to come in and actually do that. What you find out is the requirements aren't necessarily there yet for the B31.3 piping. You don't follow the same rigid protocols that you would for B31 piping or power piping or certainly Section 8 vessels. So you end up using a hybrid of the manual shear wave techniques or the manual shear wave code requirements, you know, workmanship-based acceptance criteria with the phased array. The codes are very explicit about the requirements. Of course, the requirement for particular equipment, that is storing data, being able to store data in its raw format such that it can be interpreted by third parties, but also the procedure qualification process. And in my opinion, right now it's just too tedious. Been able to maximize efficiency by building a stockpile of mock-ups and qualification blocks, and over time that gets easier and easier. But it is my hope that one day that we'll truly be able to do these kind of qualifications with beam tool programs and analytical modeling, rather than actually building these blocks and doing it out there in the field. So most people end up finding themselves over here, in my opinion. The authors are certainly over here, but it gets real complicated for level 2 technicians. I think that's part of the reason that level 3 data review is mandatory when using the code case. Certainly in Section 8 pressure vessels and power piping, level 3 involvement's pretty critical. So I don't know if you know what the ratio is of level 3s out there to level 2s, but I'll just say that, you know, for every 90 level 2s, there's probably one level 3. So if you got 90 technicians out there and you expect one level 2 or one level 3 to analyze all of his data or all the 90 technicians' data, it gets a little tough. But what I'm referring to here is when you have to deal with coplanar flaws and stacked flaws and proximity, et cetera, and so forth. In radiography, you simply deal with density change, flaw type, and length, and location. You don't really care where it's at in the weld. It doesn't affect the accept or reject at all. But in ultrasonics, it does. So some feedback. UT is not equivalent to RT. RT is less sensitive to more serious defects, lack of fusion, cracks, and more sensitive to less serious defects, porosity, slag, volumetric flaws. The opposite is exactly true for the UT. It's more sensitive to planar flaws, less sensitive to porosity. I'll give it porosity. Slag, certainly not, but then Toft is generally the catch-all for porosity. Toft's pretty sensitive to porosity. RT looks into welds in a single plane, UT at multiple planes. UT can size for critical assessment. You can use ECA or fracture mechanics-based assessments for acceptance criteria. With RT, you're almost always on a workmanship. In the future, UT will reduce unnecessary repairs potentially. Equipment calibrations are paramount. So like I said, with radiography, there's really nothing to calibrate. So some of the feedback we get from owners and fabricators is, it all comes down to technician skills, equipment, and the calibration. And that's still true, and I think it'll always be true. Scan plans, encoded scans versus non-encoded scans, much like calculating the shot time for RT, in this case you're calculating scan plans, beam coverages. It's one thing to actually calculate and do the beam coverage, tell what you need, then it's another thing to make sure that that beam tool or that beam scan plan got executed. So one, this is what it requires, and two, how do we know that got done? Some of that, is covered in some of the workflow process that the previous speaker was talking about. Reporting, prepare the standard laptops, templates, data transfer, memory sticks. Now you can pretty much beam data, indiscriminately anywhere you want, which you can with DR and CR as well. But a technician can actually be in the field, acquire a scan at the end, push a button, that data is immediately transmitted to a central location, an email alert sent out to the level 3, and level 3 can pull the data up, review it on the spot. So there are some advantages there the clients are liking. Project requirements, You know, with RT, there's not a whole lot you got to worry about. You get an RT cert, make sure that, you know, you might validate what source is coming out there. You might need a strong source. In some cases, you might need a very weak source. I had one particular application where the client said, I need a 10 curie source, so I don't have to barricade no more than 80 feet. So how do you get a 10 curie source? Well, you either wait and hope to find one, or in this case, we bought a 1 wafer source. Typically, a 100 curie source has 10 wafers. Each wafer is 10 curies. So in this case, we had to buy a 1 wafer source to get a 10 curie source, so that we could actually do the shot without shutting down all these people. They weren't yet set up to do UT. Fabricator, owner user, piping layouts, access to the weld, acceptance of procedure. Basically, you got to acknowledge and sign off on that procedure. Unlike radiography, in this case, you're assigning that the procedure's been qualified, the technicians, the techniques, through the mock-up or whatever it happens to be. In summary, advanced UT such as phased arrays increasingly becoming the preferred replacement for RT. Higher productivity, non-impacting the construction, safer execution, preferred documentation. Owner user achieves baseline data. That's another hidden benefit there. Many times what happens after these things go in service, they're not inspected with radiography ever again. Normally that's an in-service UT inspection. So if UT was done up front, it makes it much easier to compare ultrasonic from the pre-inspection to the post-inspection or subsequent in-service inspections. That about covers it.
Thank you very much, Dave.
You're welcome.